Okay, here's a student argument question. When you get a question like this, it's best to develop your own argument first so that you're not convinced of something that might be incorrect. So looking at our system here, it seems like we have water flowing through this larger area region. Notice that this is a diameter measurement. And then that water is going to go uphill, so I'm thinking maybe a Bernoulli's equation might be appropriate, so that at this higher point, the pressure will be less, and it will be less because we have a even smaller diameter here, which means we know our water will be moving even faster here than it was down here. So let's cut these arrows down in size a little bit. Okie dokie. The next thing I'm going to do is just write down my equation. That's going to help me think about it all. So I know that Bernoulli's is going to come up here, because anytime you see a tube and fluid, that's pretty much the way to go, flowing. So now let's go ahead and read student Y. So student Y claims down here that the pressure at point B is greater. We're like, I don't think so, because this term is bigger for B and this term is going to be bigger for B. So I think that's probably wrong. And that at point A, because the water is moving faster at B. This seems to be good. And why is that good? That's some continuity. Okay, so indicate any aspects of student Y's claim that are correct. So we say that student Y, that the water is moving faster at B is correct. Doesn't tell us to justify, so move on. Indicate any aspects of Y's claim that are incorrect. So here they say that PA is going to be less than PB, and we disagree. It's incorrect because so we're going to disagree. We're going to say it's incorrect because in Bernoulli's equation, and then we can write this here, these two terms are larger, so this pressure will be less. Okay, nice. Indicate any aspects of student Z's claim that are correct. Student Z claims the speed of the water is less at point B. Well, that's going to be wrong. So keep going. Because of conservation of energy, some of the water's kinetic energy has been converted to potential energy. So they're saying that the potential energy, UG, at location B is greater than the potential energy at location A, and I do agree with that. Now let's go to incorrect. So incorrect, they say that the speed of the water is less. So they say that VA is going to be greater than VB. And we know that that's not true because of continuity. And you can either say the name of the equation or you can just go ahead and write it out, which we already figured would come into our thinking, and we'd already written it down above. And so we can just say that as VB must increase because the AB is less. Now what else is interesting here is that conservation of energy comes up, but there is work. So energy is not really conserved because there is work from the delta pressure. And some of the water's kinetic energy has been converted into potential. They're claiming that the delta KE is going down, but it's delta KE is actually going up, right? Because the velocity at B is greater. And there is a PB does not equal PA. So there's a pressure difference. Doing work. All right, now it has to calculate the following at B. So we're going to need the two equations that we're using above. So let's go ahead and look at them. Now we'll use continuity to get our speed first. When we do that, we'll watch out because as we fill in our areas, we're going to use these numbers here. These are diameters, and we'll keep each one in centimeters. It will be fine. So let's go ahead and fill that in. Here we go. So here we'll have the area at location A. We're going to do pi r squared. So take that diameter, cut it in half, and square it. VA is 0.5. I just read that from the problem statement above. At AB, pi, take that diameter, cut it in half, squared, and VB Okay, cool. We can solve for VB. Notice I made a mistake writing 2.25 instead of 2.5. And we should get 1.4 meters per second. Notice that the meters per second and the 0.5 is what carries over to these units, meters per second. Now let's get the pressure in the pipe. So that's going to go to our Bernoulli's equation right here. Okay, and we'll go ahead and fill it in. So let's take the information from above in the problem. All right, so PA is 2. Let's call that height 0. Let's see how high it is. Looks like point B is 5 meters above A. So rho G Y2 plus 1/2. And we get that PB is 1.5 times 10 to the 5th Pascal. All right, and now they AP swing it. So it's the same problem, but also completely different. So they're going to have the valve close off at the end of the pipe. Let's see what that looks like. So let's close this here. And so now we just have this whole pipe filled with water, and it is stationary. It wants to know what the absolute pressure is at point A. So A is right here. We can still use our Bernoulli's equation without any flow if we like. So you can say the pressure at A plus 0, and we're no longer flowing, will equal the pressure at the top. Let's just go all the way up to the atmosphere here. So we'll equal now P atmosphere plus rho G H. And we'll use this entire height above. So when we fill that in, we get, notice that P atmosphere is just 1 times 10 to the 5th. They don't write it as 101 kilopascals. All right, next let's look at this air bubble forming. So air bubble forms down here. Now what happens to air bubbles? They're very light. So we're going to draw a very small mg. You may also label this with a W or FG. Okay, those are acceptable labels. Now, bubbles experience a lot of buoyant force. Why? Because they have a very large volume. They can displace a lot of water. Right? So if you want to label that FB, that's good. And if you wanted to calculate it, what it was, it's density of water, gravity, volume of the bubble. So key here is to make sure your buoyant force is bigger than your mg, because you're trying to draw the lengths of the vectors. Anytime you see a diagram with the grid there, you need to make sure that you express the bigger vector as looking bigger.